In this video, I want to discuss linear inequalities and a couple notations called set builder notation and interval notation, which are notations you might have run into before previously. Okay, the first thing I'm going to do in my first example here is just imagine the real number line here, okay, as you can see part of it here. Let me get a little colored pencil out here. Okay, here I've got the real number line. Now, here I've got something I call set builder notation. You see these little curly brackets here? There's one, and there's another one. This indicates that you're dealing with a set. Those are actually called braces. Braces, like that you put on your teeth there. Okay, well, not exactly what you put on your teeth, but there it is, the same word. Okay, those are called braces or curly brackets, as some people call them. I'll call them braces. This is going to be read in the following way for us. When you see those curly braces, the braces are curly brackets, what you're going to do is say the set, okay? That automatically means you're dealing with a set, okay? And then you see here, you're going to universally quantify this. You're going to say the set of all, and this will assumably be real. So we'll say the set of all real x, and this little symbol going straight up, sometimes people will use a colon for that, but that's a vertical, just a vertical line. That means such that, okay? And then you have a description here. So what set builder notation does is give you a set of elements by describing that set somehow, okay? And we're, of course, going to be concerned with sets of real numbers here. Okay, so this, I like it right here, this is in set builder notation. This would be the set of all x such that x is less than 2, okay? Now, if you imagine actually graphing that on the real number line, that would include everything to the left of 2, okay? So I've shaded in everything to the left of 2. Now we're talking about the real numbers, so it's not just 1, 0, -1, integers. It's all the real numbers. So like 1.993 or 1.99996 and stuff like that. So everything to the left of 2 is everything less than 2. For 2 itself, 2 is not less than 2. So to mark the right endpoint of this set here, what people will sometimes do is just use an open dot at 2. That indicates you're not actually including the 2 because it's open there, okay? So that's open, that's one notation. Or here's another common notation that you will see in some books for the same set. Instead of using an open dot at 2, they will use parentheses, okay? They will use parentheses. All right, so you've got parand there, or what the singular is for that. Okay, these mean exactly the same thing, and they mean the same as that. Okay, so we've got set builder notation, and then we've graphed that set on the real number line. I'm calling this example 2 because this is a new notation here. Okay, exactly this same set, the set of all real numbers less than 2, is written in something we call interval notation in the following way. Okay? Now, you read from left to right, and the smaller numbers are to the left. Okay? So, this is going to be everything from -infinity up to 2. Now, in interval notation, just like this notation above, if you're using parentheses, that means you're going up to 2. Okay, up to that whatever that number is, but you're not including it. So it's like this open dot situation. Okay, so this means we're going all the way up to 2, but not including 2. Likewise, notice on the left-hand side we use parentheses also. That's because we're certainly not including -infinity as part of our set, because -infinity is a concept that really doesn't exist as a real number itself. Okay, alrighty. So these mean the same thing. This is what we're going to have or be calling an interval notation, And then this second one here, I've got a set builder. Okay? Alrighty. Let's consider some other ones here. Suppose I take example 3 here. I'm on the real number line, and you see what I've shaded in here. Okay, or I hope you see what I shaded in. Everything from -1 to 2, but over on the left-hand side at -1, you notice that I actually have a solid dot. Okay, it's filled in. That indicates that I'm including -1 itself. Over on the left-hand side, once again, I've got an open dot, indicating that I'm not including 2. So you can see I'm including everything from what? -1 to 2, or everything between -1 and 2, but including -1, but not including 2. So we would say in set builder notation, this is the set of all real x, or the set of all x if you want, because real is implicit. The set of all x such that, right? Remember that? Such that -1 is less than or equal to x is less than 2. Okay? All right, so that's precisely that set graphed above on the real number line. Okay, now here's another notation instead of solid dots and open dots like we were doing before. Remember, where you have a solid dot, you're going to be using parentheses. So I've got a right parent here. But on the left-hand side, where I'm actually including the -1, I use square brackets rather than parentheses. That indicates that I'm actually including that point upon which it falls. So this would be in interval notation also, which you can see is closely related to this. This would be the interval notation. It would be square bracket, -1, 2, parentheses, okay, or parent. Okay, so this means exactly this set here. Okay, the interval notation you can see is kind of compact and convenient compared to the set builder notation. Okay, let's keep going here. Let's take a look at example 4. Take a look at that graph. I've got what? I'm solid filled in at 0, and I'm taking everything to the right of that. That means everything greater than 0. Okay, so this would be the set of all x such that x is, I made a typo. This would be the set of all x such that x is greater than or equal to what? 0. Okay, greater than or equal to 0. Okay, we got to have that equal sign because we have that filled in dot, right? Okay, and here's our other notation on the real number line. We'd have what? Square bracket at 0, filled in everything to the right of that. So we're going in interval notation, square bracket, 0, comma, infinity, and parentheses. Of course, when you come out here, you're not actually including infinity as part of your set. So use parentheses there. It just means there's what? There's no bound on the size of the elements of the set to the right, okay? So we're not really treating infinity as a real number as such. Just that lazy 8 symbol here. Let's look at example 5, okay? Here I've got some set I'm looking at here. I would call those 2 intervals, okay? But they're disconnected, okay? There's 2 separate ones here. Now look at this one. I have a solid dot at -3 and an open dot at 0. So what would I have in my interval notation? I would have square bracket, -3, comma, 0, and then parentheses, right? Okay. And then this other side, I'm going from what? 1 to infinity, but I'm not including 1. So I use parentheses, and then 1, comma, infinity, parentheses again, okay? Now, I want to put these together in a single set, okay? Because this is maybe the solution of some problem. It's the set of all values of x that lie in this set here. I want to throw them together in one set, and so I use this operation here. I just indicate that by putting this sort of U symbol here, okay? And the word is union, okay? So it's this set union this set, okay? The U there should remind you of the word union. Okay? All right? Don't put a hook on it. It's not literally a U. Don't do that. It's just like a smiley face without eyes. Okay? That's union. That would be our interval notation. Now, how would we do it in set builder? It would be the set of all x such that, what? -3 is less than or equal to x is less than 0. Okay? Or satisfies what? That x is greater than 1. Okay? Another way of saying that is what? 1 is less than x. I wrote that here. That means exactly the same thing as that. Right? Okay? Let me emphasize here why this is an or statement. You're talking about the set of all x that satisfy this condition or satisfy this condition. Okay? There are you wouldn't say and there. That would be a logical and. Okay? If I had and there, we would have the empty set because there's no values of x that satisfy this condition and satisfy this condition. Okay? I hope that makes sense to you. So let's think of this in terms of logic here. Okay? It's a set of all x that satisfy this condition or satisfy this condition. Or in some cases, possibly both. Okay? That certainly it can't hold in this case, though. All right? And notice here, like I said, I just changed the direction of the inequality. That's fine so long as I also, interchange the 1 and the x, right? Okay? This is just saying 1 is less than x. This is saying x is greater than 1. They're saying the same thing in two different ways. By the way, people usually don't go like this because it's sort of a waste of time. For this set over here, they would not write 1 is less than x is less than infinity. I mean, that makes sense, but this part, all real numbers are less than infinity, so it's enough to say 1 is less than x. Okay? All right, well, I hope you understood this. Just playing around with notation right now. Here I've got the real number line. I've shaded in everything, but except at 0. Notice I have an open dot at 0. Okay? So this is the set of all x such that what? X is less than 0. That's the left-hand bit. Or what satisfies the condition that x is greater than 0. Okay? A shorthand for this, in this case, would be the set of all x such that x is non-zero, right? All right. Now, what would this be in interval notation? Now, you're going from left to right. Okay, in this first set, there's no limit to the left, so you would have what? Parentheses, negative infinity, okay? Then comma, and you run up right up to 0, but you're not including 0. So you go comma 0 with parentheses because you're not including the 0. Now I'm going to write what? Union, because I want to put these together in one set, okay? And then I'm going from what? From 0 to infinity, right? Everything greater than 0. So parentheses, 0, comma, infinity. No limit to the right there, okay? So this would be the interval notation. And when we work these problems, we often like to write our answers in interval notation, but I'm giving you practice in both notations right now. Let's look at example 7. The set of all x such that x is 2. Okay? That's just a funny way of writing this set. 2. Okay? All right. All right. That's a wordy way of writing the set 2. Okay, if you were to graph that on the real number line, you would just put a filled in dot at 2 and nowhere else, right? Okay, what would be the interval notation in that case? Well, your starting point is at 2, your ending point is at 2, and since you're including 2 at both ends, you want to use square brackets, okay? So it would be square bracket 2 comma 2 square bracket. Again, that's a kind of a long way of writing what? The set of all elements consisting of 2, okay? Alrighty. So neither of these notations are particularly efficient in the case of just a single element here, but it can still be done, okay? All right, let's now start talking about the linear inequalities. I'm sure you've run into this before back in your previous math classes, So this should be pretty much a review. Let's talk about the rules of inequalities here. You can subtract. You can add or subtract the same quantity on both sides of an inequality without changing the direction of the inequality. Okay? All right. Number two, you can multiply or divide on both sides of an inequality without changing the direction of the inequality if the quantity is what? If the quantity is positive. Okay? All right. If the quantity is positive, then you can divide or multiply on both sides by that quantity, and it will not change the direction of the inequality. However, if you divide or multiply on both sides of an inequality by what? Remember this? A negative number. Okay? A negative number, then the direction of the inequality changes. Okay? All right? So it's only this third case that's kind of weird. If you're dividing or multiplying by a negative number on both sides of an inequality, that will change the direction of the inequality. Okay? All right. Well, let's just use these rules to solve some simple inequality problems and write our answers in interval notation. Let's go ahead and solve this. 2x minus 3 is less than or equal to 7. Okay, on some of these I'm going to start out writing some of the steps. You can skip these and you'll still be fine. But the idea is I'm going to isolate x, just like I would if that was in a strict equality, an equation in other words. Okay, I'm going to add 3 on both sides. Okay, and that should not change the direction of my inequality. And I would get what? The minus 3 and the positive 3 canceling. That's why I did it. So that on the left-hand side I get what? 2x. On the right-hand side I just get 10. Now I want to isolate x, so I'm going to divide on both sides by 2. Now 2 is positive, right? 2 is positive, so that means this is not going to change the direction of my inequality. Okay, so divide on both sides by 2. Notice it's still less than or equal to sign all the way through here. Okay, so what I would get, x is less than or equal to 5. If I was to graph that on the real number line, I'd go what? I would fill in 5 because I've got an equal sign here, right? I'm including 5. Okay, but I want everything less than that as well. So I've got a solid dot at 5, and I'm going to what? Shade in everything to the left of that as well. Okay, if you didn't want a filled in dot, if you wanted to use the other notation, okay, you would use what? A square bracket, a right-hand side square bracket, and then fill everything in to the left of that, okay, since it's less than. Okay, now we've got less than or equal to. What would this be? Well, there's no what? There's no limit as you move to the left here, so I've got parentheses, minus infinity, comma 5, square bracket, final answer, okay, in interval notation. Alrighty, okay. Oh, up here, by the way, the set builder notation would have been the set of all x such that x is less than or equal to 5, okay. I would have just taken this part out. Okay, that would have been the set builder way of writing it. Let's look at an inequality that's a little more difficult here, but it's not too bad. Still, again, it's going to be a linear inequality, so you're not going to have squares of x, and you're not going to be taking quotients of functions of x. Okay, just it's simpler than that for these ones. Solve this. 7x minus 3 is strictly less than 11x plus 6. Okay, alrighty. Now I'm going to show you actually two different ways to work this, one of which illustrates this up here. If you divide on both sides by a negative number, you change the direction of the inequality. Okay, here's what I'm going to do first. Let's try the solution this way. I need to isolate x, right? So what I'm going to do is actually add 3 on each side, and I would get what? 7x is strictly less than 11x plus 7. Okay, I could just say less than rather than strictly less than. That's just emphasis here. Okay, So 7x is less than or equal to 11x plus 9. Okay? Now I need to isolate the x, so what I'm going to do here is subtract 11x on each side. Now 7x minus 11x is minus 4x that you see there, and that 11x is gone over on the right-hand side of the inequality here. Now I've just subtracted on both sides. That's not going to change the direction of the inequality. So it's still less than there. I've got negative 4x is less than 9. Now I need to isolate x, so I'm going to divide on both sides by negative 4. When I divide on both sides by negative 4, immediately the direction of the inequality will change. Okay, don't wait around to change it. The moment you're dividing on both sides by negative 4, you should have that direction switched. That's why I'm taking an extra step going from here to here. Okay? Simplify the statements now about x. This would be what? In set builder notation, if we wanted to be wordy, so to speak, the set of all x such that x is greater than negative 9/4. Okay? If you think about that mentally on the real number line, you're going what? Parentheses, minus 9/4 out to infinity. Okay? Alrighty? Now, that's our first solution. Let's talk about the second possible way of solving this. Maybe you would rather do this, gather the x values on the other side. Let me show you this is perfectly consistent here. Okay, so in this case, here's my starters. I'm going to start out the same way again. I'm going to subtract 6 on each side first. So I've got 7x minus 9 is less than 11x. Then I'm going to subtract 7x on each side. I've got negative 9x is less than 4x. Now 4 is positive. So if I divide on both sides by 4, the direction of the inequality will not change. And I've got negative 9/4 is strictly less than x. Okay, now you can see here, this looks kind of strange. It's like saying brown is the hat rather than the hat is brown, right? Usually in most sentences we think about, at least in English, the subject coming first. So you want to talk about x first. Okay? Well, the alligator's mouth is open to the x, so if I turn this around here, I could say something that's equivalent. I could say x is greater than negative 9/4. These two are saying exactly the same thing. Okay? Now notice that's exactly the solution I had before. Yep, there it is up there. Okay? So x is greater than negative 9/4. Again, the corresponding interval notation. All right, let's talk about different set operation here. We've talked about union, remember that? Bringing two sets together. That just means you take all the elements in the two sets and you throw them together in a single set. And we said that corresponds to a logical OR statement. The set of all elements that are in this set or in this set. And OR is used in the non-exclusive sense, being or both. Okay? That's just what we usually do in mathematics. Anyways, let's come back. Intersection and double inequalities. I'm going to show you here. If A and B are two sets, okay, they don't have to necessarily be numbers. They could be anything. What we call the intersection of A and B, written this way, okay? Notice it's upside down from the union symbol. It's turned over. It looks like a frowny face without eyes, okay? It's written A intersection B, okay? Is the set of all elements common to both A and B. If you think about two roads intersecting, okay, that means what? The part of the roads they have in common, right? All right. All right, so it's a set of all elements common to both A and B. Let's take example 10 here. Suppose the cap set A is ABCD and the set B equals BDE. Okay, I'm taking a break from numbers here for a second. What's the intersection of A and B, or A intersect B, or A intersection B? Okay, which elements are common to these two sets? Well, it turns out little a is not common to both of them. Little a is part of cap A, but it's not part of B. How about little b? Yep, little b lies in both of them. So that's going to be in the intersection. C? No. C is in A, but it's not in B here. Okay? And then D is common to both. And you will see here that B and D are the only elements common to both cap A and cap B. So we would write A intersection B is the set. Notice those braces, right? Curly brackets. And then I just listed the elements there, B comma D. By the way, if you create a set by writing, just listing the elements, that's sometimes called roster notation. Okay, think about a roster, just a list, right? Let's talk about exercise 11 here, example 11. Okay, suppose A now is a set of all real numbers x such that x is greater than 3. And suppose that B is a set of all x such that x is less than or equal to 6. Then A intersection B is the set of all real numbers x such that x is greater than negative 3. And so they satisfy that condition and satisfy the condition that x is less than or equal to 6. Okay? All right, let me jump down here before I look at this part right here. Here's A, right? Here's A. I've kind of graphed it so it's floating above the, here's x, above the x-axis, okay? But that's what A would be, right? Okay? And here is what B would be. I didn't label that, sorry. This is B here. This would be what? The set of all values of x which are less than or equal to 6, okay? So I've written that below. The intersection of the two would be the set of all values of x common to both of those, and that's what I'm trying to drive at here. That's where these overlap, right? Where these are overlap, where they intersect, okay? You could see it would be what? Everything from -3, not including -3 though, because that's not part of A. Everything this direction, okay, so greater than -3, all the way up to and including 6, okay? So if I intersected A and B, this is the set I would get, okay? Another way to describe that would be what? The set of all x such that -3 is less than x is less than or equal to 6. And I guess I should throw in the interval notation, right? Okay, this would be what? Open at -3, okay, comma, 6, and then closed bracket or square bracket, okay? So that corresponds to this set right there. That's our interval notation. Okay, let's look at example 12 here. I'm making the inequalities a little bit harder here. Suppose you try to solve this. Find all values of x that satisfy this condition. -7 is less than or equal to 2x plus 3 is less than or equal to 12. Okay? Now here's what I'm going to do. Since I've got two inequalities, okay, I'm going to break them up. I'm looking for x that satisfy both conditions, so I'm connecting this with an and statement. So it's a set of all x that satisfy this and satisfy this. Okay? You're not going to take values of x that, unless they satisfy both of them. Okay? Now, if I was to give you this inequality, -7 is less than or equal to 2x plus 3, that'd be pretty easy. What would you do? You'd subtract 3 on each side, right? And then divide by 2. That's what I did here. Okay? Now, if I look at 2x plus 3 is less than or equal to 12, I would subtract 3 on each side, right? And then divide by 2. Notice that those are exactly the same operations in both cases, okay? In other words, I did what on both sides? I subtracted 3 on both sides, and then I divided the result by 2 on both sides, right? Okay? So anyways, our conclusions are -5 is less than or equal to x, and x is less than or equal to 9, okay? You could graph those like we did up here, but I think you can see what I'm driving at here. The intersection of those two sets would be what? The set of all x such that what? -5 is less than or equal to x is less than or equal to 9/2. Okay? So that we could actually write this in interval notation, square bracket -5, comma 9/2 square bracket. Okay? All right? This was kind of a long way, breaking this up into two inequalities. This could have been done more compactly by just writing this, okay? Subtracting through my 3 all the way through the inequalities, like this, and then dividing by what? And then we got those conclusions, and to then divide by 2 all the way through. Remember, 2 is positive, so the direction of the inequalities don't have to change. The reason why this worked, and I could write this compactly like this, is because I was using what? Exactly the same operations to isolate x in each case, okay? Subtracting the 3 and then dividing by 2, okay? Now I'm going to show you a different problem. This will be the last question here. I'm going to show you a different problem where we have more compound inequalities like this, and we have to write it this way essentially, okay? I have to use that and statement. This isn't going to work up here. What I did, this little compact notation, and the reason why it's not going to work is because I have to use different operations on each inequality. Okay, but this is essentially what we're saying. We're looking for the set of all x such that 2x minus 3 is less than or equal to 4x, and 4x is less than x plus 9. Okay, so I just broke that into 2 inequalities, okay, and we'll deal with the and statement here, bringing them together in a minute. Okay, let's go ahead and solve this one here. The way I'd solve this one is to do what? Subtract 2x on both sides, and I would have negative 3 is less than or equal to 2x, and then I'd divide both sides by 2. Okay, 2 is positive, so we'd have what? Negative 3 halves is less than or equal to x, okay? Now over here, I've got 4x is less than 9 plus x. Here, I'm going to do what? I'm going to subtract x on both sides, yielding 3x is strictly less than 9. Okay, that's different than what I did over here. I didn't subtract x on both sides over here. Okay, that's why I have to break it up here. Anyway, so I get to 3x is less than 9. We said divide on both sides by 3, and we get x is less than 3. And now let's put these together here, and you can see I can squish them together now. I've got what? Negative 3 halves is less than or equal to x is strictly less than 3. In interval notation, that'd be square bracket, negative 3 halves, comma, 3 parentheses, okay? So you see, sometimes you do have to take a compound inequality like that and actually break it up, okay? And other times you don't. Alrighty, well, I hope you understood all this. It shouldn't be too bad. Next time we'll be talking about inequalities involving absolute value.